Hello and good afternoon to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss a very important concept in operating system that is referred to as process scheduling. Consider there exists multiple processes waiting for allotment of CPU time. So, where there is contention among the processes for allotment of CPU time, such scenario calls for deployment of efficient and effective mechanism for allotting the CPU or CPU time to the processes. Now, such mechanism is referred to as scheduling. So, in simple context, scheduling is a mechanism or a framework deployed in order to assign or allot CPU or CPU time to the processes that are waiting for execution. Now, you may be wondering on what criteria the programs that are capable of scheduling processes schedule CPU time or assign CPU time to the processes. So there are various fundamental bases that may be taken as the decision point for deciding on how the processes are to be scheduled or assigned the CPU time. For an example, CPU time may be assigned to the processes on first come first served basis. So whosoever comes first will be assigned the CPU first. So that can be one of the simplest mechanism of assigning process CPU time to the processes. Likewise, allotment of CPU can be based on certain priority. So you assign priority with the jobs. So the assignment of CPU to the processes will be based on the assigned priority. So the high priority processes will be assigned the CPU first. Subsequently, the low priority processes will be assigned the CPU at later point in time. Or it can be based on certain quantum value on a round-robin basis. So everyone gets a chance for execution for a certain period of time or certain time slice. Or it can be based on a concept like shortest job first. So whosoever has the shortest execution time may be allotted the execution time first. So there are several criteria based on which the CPU or CPU time can be allotted to the processes for execution. So for now, just remember that process scheduling is a framework that allows for scheduling or allotment of CPU or CPU time to the processes that are waiting for execution. So process scheduling is a fundamental and essential part of multi-programming in an operating system. So when multiple programs are competing for the CPU time at the same, so this is what we have discussed. So when multiple programs are competing for the CPU at the same time and awaiting or waiting for execution, in such situation the decision for selecting an appropriate process for execution is called as scheduling. Okay, so when multiple programs or processes are competing for CPU at the same time and waiting for execution, in such situation the decision for selecting an appropriate process for execution is called as scheduling. So as I've already said, some of the scientific basis or fundamental basis may be first come first served, based on priority, or based on time slices, or it can be based on a concept like shortest job first. Now, who does it? It's very much important for all of us to know who does this scheduling. So there is a special program in every operating system that is called as scheduler. So the part of the operating system that makes the choice is called as the scheduler. Now what does scheduler allow? So it allows multiple processes to be loaded in the executable memory at any given point in time, and the loaded processes then share the CPU using time multiplexing. So this is what scheduler does. So that means there are schedulers that are capable of loading the job, there are schedulers that are capable of assigning the job for execution. So here just see there are two important contexts that has been reflected in this particular statement. So it allows multiple processes to be loaded in the executable memory at a given point in time, or at any given point in time. So there is a type of scheduler that is capable of loading the job into the ready queue, and there is the loaded process, and then the loaded process shares the CPU using time multiplexing. So there is a scheduler that is capable of scheduling the job or assigning CPU to the job. So just see there are different types of schedulers that are there in the operating system that are capable of performing purpose specific tasks. So just a hint in this particular point is that there can be different types, or there are different types of schedulers that work in the operating system. So in this particular slide, what we have learned is that scheduling is a mechanism or a framework that allows the operating system to schedule multiple processes or allot CPU or CPU time to the processes that are waiting for execution. Now such decision is based on certain criteria. So criteria may be first come first served, or priority based, or time slice based, or it can be shortest job first. And then we learned that this is performed with the help of a program that is called as a scheduler. And we have also learned that schedulers are of different types. Some are responsible for loading the job that needs to be executed, some are responsible for preparing the job for execution. So we will now discuss the constituent structures that are used in scheduling. Now the next important concept that you need to understand regarding scheduling is the importance of scheduling queues. Now there are different types of queues that are associated with scheduling. Now some are capable of keeping track of the jobs, some are capable of keeping track of processes that are ready for execution. So depending upon the purpose, again I'll repeat it, depending upon the purpose, there are different types of queues that are associated with scheduling. So now let us try to understand what are the different types of queues that are associated with scheduling. Now all the processes that enters into the system are sequentially placed in the job queue. Again I'll repeat it. All the processes that enters into the system are sequentially placed in the job queue. So this is one of the data structure that is used in order to store the processes. So all the processes that enters into the system are sequentially stored in the job queue. Now the ready processes residing in the main memory and waiting for execution are kept in the list called as ready queue. Okay, so now this is the second queue that is there associated with processes. Now ready processes residing in the main memory and waiting for its turn for execution is stored in the list that is called as ready queue. So this is the second data structure that is there associated with job. So first one is the job queue, second one is the ready queue. Now ready queue is generally a linked list with its header containing pointer to the first and the last PCB in the list. Now as we have learned, process control block is a data structure that stores state information about a process, a unique process. So PCB, process control block, is created for every individual process. So it is to be understood that PCB is associated with the process. So when there are multiple processes ready for execution, then it implies that ready queue is nothing but a data structure that keeps track of multiple PCBs. So it is to be understood that ready queue is a queue of PCBs. So ready queue is generally a linked list with its header containing pointer to the first and the last PCB in the list, because the first PCB will keep track of the first process that is awaiting execution, and last PCB will keep the status information of the last process that is preparing for execution. So ready queue is nothing but a queue of PCBs that refers to multiple processes that are awaiting allotment of CPU time. So ready queue is generally a linked list with its header containing pointer to the first and the last PCB in the list. Now the PCB of the process includes a pointer field that points to the next PCB in the ready queue. So this is understood. So one PCB will point to another PCB that is there in the list, because as I've said, ready queue is a linked list of PCBs. So every PCB will have a pointer to the next PCB that is there in the list. So this is what this particular point implies. So the PCB of a process includes a pointer that points to the next PCB in the queue. Now likewise, processes that are waiting for device to be allotted when it becomes available are placed in the device queue. So for an example, if a process X is awaiting allotment of a IO device, say for an example a printer or for a scanner, so that process has to be placed in some queue that is waiting for allotment of IO devices. So that queue is called as a device queue. So process waiting for device to be allotted to it when it becomes available is called as device queue. Now device queue is the third type of queue that is associated with process. So there exists a device queue with every IO device. So this is to be understood. So every IO device has a device queue where the process will be placed when the process is requesting for allotment of that IO device. So this is the third data structure that you have, that is called as device queue. The first one is job queue. Job queue keeps track of all the jobs that are to be executed. So all the job that enters into the system is sequentially placed or are sequentially placed in the job queue. Then when the job is or the process is ready for execution, then the process is placed in the ready queue. Now subsequently, if a process is requesting for allotment of device, the process will be placed in the device queue. A new process is initially placed in the ready queue. It then waits in the ready queue until its selection is done for execution. So any process that is awaiting execution is placed in the ready queue, and then it waits for its time of allotment of the CPU. Now here it is to be understood that it's not only a new job entering into the ready queue, but a job that has been interrupted and is waiting for the execution to resume is also placed in the ready queue. So this is also to be understood. So ready queue is a queue that is not only used for storing a job that is waiting for execution, that is new. It is also kept. It's also used in order to keep the jobs that has been interrupted and is waiting to resume execution or waiting for allotment of CPU time. So ready queue is used for both the purpose here. So we have understood here that there are three types of queues that may be associated. You have job queue, you have ready queue, and you have device queue. So let us now try to understand what may happen when the process is executing. So let us consider that a process is allotted a CPU, or so it may so happen that you may have multiple CPUs in a computer system, or you may have a single CPU in a computer system. So let us try to understand what may happen when a process is executing. So once a process is assigned to the CPU, or once the process is assigned with CPU time and is executing, one of the following several events may occur. Again, I'll repeat it. Once the process is assigned to the CPU, or once the process is assigned with certain CPU time and is executing, one of the following several events may occur. First one is the process may issue an IO request. So the process that is currently being executed wants allotment of the IO device, okay, right, in order to perform some activity. So the process issues an IO request. So when a process issues an IO request, the process is placed in the IO queue, okay, because IO queue is a data structure that is associated with the IO devices that keeps track of all the processes that are requesting for it. So the process issues an IO request. So once it issues an IO request, it is placed in the IO queue. the process may create a new subprocess and wait for its termination. So this also may happen. The process creates a new subprocess and waits for its termination. So, for an example, you are running a program that performs sorting of integer array. So you may create a process for reading the content into the array, right? Okay. So now what the main process has to do? The main process has to wait for the subprocess that is capable of reading the content into the array to terminate. So that's the way, that is an example. So the process creates a new subprocess and waits for its termination. Third one, the process is forced to release CPU assignment as a result of interrupt. So as I've said, so when a process is being executed and there comes in a very high priority process that cannot be ignored, so what you need to do is you need to assign the CPU to the high priority process, and what you need to do is you need to wait unless the high priority process completes its execution, and then what you can do is you can resume your execution. So the process is forced to release CPU assignment, and as a result of interrupt, so in such situation the process will be placed back to the ready queue. Next one is, a process continues this cycle until it terminates. So it's also to be understood, a process continues this cycle until it terminates. So consider a situation that the CPU is allotted to the various processes based on certain timestamps or quantums. Say, for an example, for every 2 nanoseconds the process in the process queue will execute. Okay, so every time, so once the process finishes its allotment of 2 nanoseconds, again it needs to go back to the ready queue and be prepared for the execution. So this particular cycle repeats. So a process continues this cycle until it terminates. So upon termination, it is removed from all the queues and has its PCB and resources deallocated. So this is what we have understood in the previous class as well. So a process continues the cycle of entering into different queues until it terminates, and once it terminates, it's removed and its PCB and all the state information as well as the resources are deallocated, and the state information is lost and the resources are deallocated. So this is what happens. Now let us try to understand the same with the help of a very simple schematic diagram. So here we have multiple jobs. We have job 1, job 2, job 3, job n. So then these jobs are placed in the ready queue, because these jobs, assuming that these jobs are ready for execution, so these are placed in the ready queue. So sequentially the jobs are assigned the CPU, right? Okay, so this is to be understood that the jobs that are there in the ready queue are sequentially assigned the CPU, or it may be assigned based on certain criteria. So the way how the scheduler schedules the processes on what criteria. So for now, just assume that the jobs are placed in the ready queue and these are assigned the CPU. So upon assignment of CPU, a process may make an IO request. So if a process makes an IO request, then the job will be placed, or the process will be placed in the IO queue as understood, and then once the IO task executes, it will be placed back to the ready queue. Now why it has to be placed back to the ready queue is because it is to be understood that while the CPU is being while the job that has come in, that has made an IO request, is no more making use of the CPU, what can happen is that the CPU can be assigned to some other process rather than keeping it idle. So it's to be understood that the CPU has to be optimally used. So it's to be understood that whenever a process is interrupted, or whenever a process is making an IO request, or whenever a process creates a subprocess, in due course of time, the CPU should not be left unutilized. So in order to prevent that, CPU can be assigned some other process during the time when the process are waiting for the availability of IO devices, or process are waiting for execution of subprocess, or process being interrupted. So it implies that whenever a process is waiting for something, we need to ensure that the CPU is assigned with some other process so that it can be optimally utilized. So here there are multiple jobs again. So here there are multiple jobs that are placed in the ready queue. The jobs are assigned CPU based on certain criteria. So in the first case, the process is making an IO request. So once the process makes an IO request, then it goes into the IO queue. Then eventually it executes the IO task, and then again it moves back to the ready queue in order to ensure completion of the remaining instructions that are there in the process. Now likewise, it may so happen that, as I've said, the time slice may expire. Say for an example, every process is to execute for 2 nanoseconds. So once 2 nanoseconds assigned to a particular process it gets over, then what I need to do is I need to place that particular process in the ready queue and assign the next time slice to the next process. Say for an example, here job 1, job 2, job 3 are to be executed. So let us consider that the time slice is of 2 nanoseconds. So job 1 will execute for 2 nanoseconds, job 2 will execute for 2 nanoseconds, job 3 will execute for 2 nanoseconds, and then again job 1 will execute for 2 nanoseconds. So it will go in a round robin manner. So if a situation where the time slice is expired, so again the job will have to be placed back to the ready queue and it will wait for its turn of execution. Now likewise, the third instance may be a process creates a child in order to achieve a certain task, right? Okay, so now the child has to execute, again the job has to go back to the ready queue. Now the fourth one is the process is interrupted by a high priority process. So HPP here basically implies a high priority process. So here the job or the process is being interrupted by a high priority process. So whenever a high priority process interrupts the execution of the current process has to go to the ready queue and wait for its turn for reallotment of CPU. Meanwhile, the interrupt executes. So interrupt executes and the process has to be placed in the ready queue. So just see, this is the way how the flow takes place. So there are n number of jobs that are placed in the ready queue. So depending upon what circumstances do arise when the process is under execution, whether process makes a request for IO device, a process time slice expires, or process creates a child, or process gets interrupted. So these course of actions will be initiated. So this is a very simple schematic representation of the flow that takes place whenever the process is being executed. Now let us try to understand the role of a scheduler and what are the types of the scheduler. So as we have understood that during a process's lifetime, the process migrates between different stages or different states, and this is done with the help of a program that is called as a scheduler in a very simple term. So scheduler is a program that is capable of allotting resources or CPU resources to the processes, or it's capable of placing job from job queue to. So there are several tasks that are performed by the scheduler. So let us try to understand in depth about what is a scheduler. So during its lifetime, a process continuously migrates between various scheduling queues. So this is understood. So we have understood that there are different types of queues that may be associated with the process. So there's a job queue, there's a ready queue, there's a device queue. So during a process's lifetime, a process continuously migrates between various scheduling queues. It is the responsibility of the operating system to select an appropriate process in some desired fashion when these processes are placed in the various scheduling queues. So during a process's lifetime, a process migrates among different scheduling queues that are there, and it is the responsibility of the operating system scheduler to select an appropriate queue for a particular process. So this selection process is carried out by a special program that is called as a scheduler. Now let us try to understand what are different types of scheduler. So let us first understand the job scheduler. So it initializes. So job scheduler is responsible for initializing each job. So it initializes each job and is only concerned with selecting jobs from queue of incoming queues and placing them in the ready queue. Okay, so again I'll repeat it. So it initializes each job and is only concerned with selecting job from the queue of incoming jobs and place them in the ready queue. So this is the responsibility of job scheduler. So job scheduler picks up the job from the job queue and places it onto the ready queue. Again I'll repeat it. Job scheduler is a scheduler that picks up a job from a job queue and then places it onto the ready queue. Now next one is called as a process scheduler. So process scheduler, it determines which job of those jobs that are placed in the ready queue should be allotted the CPU, when and for how long. So just see, this is very much important. So process scheduler, it determines which job of those jobs that are placed in the ready queue should be allotted the CPU, when and for how long. So which is the process that is to be allotted the CPU time, when it's supposed to be allotted the CPU time, and for how long it is to be allotted the CPU time. So this is the responsibility of the process scheduler. So it also decides when should the process execution be interrupted, executed, or a recognizable job should conclude and eventually terminate. So it also decides when should a process execution be interrupted, executed, concluded, and terminated. Now process scheduler is called as a low level scheduler, whereas a job scheduler is called as a high level scheduler. So in this particular slide, what we have learned is we have learned that during a process's lifetime, a process migrates between different scheduling queues. So to enable these migration between different scheduling queues, we have a special program that is called as a scheduler. So there are basically two types of scheduler. One is called as a job scheduler and the other one is called as the process scheduler. Job scheduler is capable of selecting a job and is responsible for placing that particular job onto the ready queue. Process scheduler, it initializes, it determines which job is to be, which job of those jobs that are placed in the job queue or ready queue should be allotted the CPU time, when and for how long. So it also decides when should the process execution be interrupted, executed, or concluded and eventually terminated. And we have also learned that process scheduler is called as a low level scheduler and job scheduler is called as a high level scheduler. Now let us learn or let us go into more detail about schedulers. So as I've said, schedulers are special software programs which handles process scheduling. Their main task is to select the job to be submitted to the system and then decide on which process is to be executed. Now categorically there are three types of schedulers, which are long-term, short-term, and medium-term schedulers. So let us try to understand the role of these three types of schedulers. Now long-term scheduler. Now long-term scheduler, which is also called as a job scheduler. We have already discussed job scheduler in the previous slide. So also called as a job scheduler, a long-term scheduler determines which program or process is to be admitted to the system for processing. Okay, so long-term scheduler is a scheduler that determines which programs are to be admitted or which program is to be admitted to the system for processing, that is from the job queue into the ready queue. So it's capable of placing the job from the job queue to the ready queue. So it controls multi-programming. Now this is a very important aspect of long-term scheduler that everyone has to understand. So as per the purpose, long-term schedulers are schedulers that determines which set of programs are to be admitted into the system for processing. That is movement of the job from the job queue to the ready queue. And it is stated categorically, it's stated that it controls multi-programming. How it controls multi-programming is because long-term scheduler is the scheduler that decides on how many number of processes will reside in the main memory. Again, I'll repeat it. long-term scheduler decides on how many processes will be residing in the memory, and as we know, only those processes that resides on the main memory will be contender for execution. Okay, so if the long-term scheduler places only 5 programs in the main memory, so there will be only 5 programs or processes that will be contending for allotment of CPU time. Right? If it places only 10 programs in the memory out of n number of programs, so there will be only 10 programs that will be contending for allotment of CPU time. This implies long-term scheduler has a very important role to play, because if there exists more number of processes in the main memory that is ready for execution, then more will be the amount of turnaround time that will be required by different jobs for concluding or terminating the execution. So if there are less number of processes, definitely less turnaround time will be there. Okay, so this is the way how long-term scheduler controls multiple programming, because it has a very significant role to play in deciding the number of processes that may enter into the main memory, which will be then executed by the processor. So the primary objective of the job scheduler is to provide a balanced mix of jobs. So we have learned that there are different types of jobs. For example, you have IO bound job, you have process bound job. So the role of a long-term scheduler is to create a perfect mix of the jobs that are being put forward into the main memory that is to be executed by the CPU, as well as the number of jobs. So it keeps track of the type of job as well as the number of jobs. So longer intervals between execution allows selection of suitable process for execution. So this is also very true, right? Okay, so if there are longer intervals between execution, then definitely there will be a proper selection of the job. So the long-term scheduler is not only responsible for containing the number of processes that may reside in the main memory for executing, that are preparing for execution, but it also has a right to strike a right balance between different types of job that may be admitted into the ready queue. So it aims to strike a perfect balance between average rate of process creation and the average rate of departure of the processes leaving the system. So this is very much important. So again, I'll repeat it. So it aims to strike a perfect balance between the average rate of process creation, that means the average rate at which the process enters into the system, and the process the rate at which the process leaves the system. So this is the responsibility of the long-term scheduler. So long-term scheduler, as the name says, it is called as a job scheduler. It determines which program are to be admitted into the system, and or that is to migrate jobs from the job queue to the ready queue, and it controls multi-programming because it decides on the number of programs that are entering into the main memory for execution. Now the second task that long-term scheduler performs is to create a perfect balance between the type of jobs that are being admitted into the system. So for example, you need to create a right balance between IO bound job and CPU bound job, and you need to ensure that there is a good interval between execution so that proper selection of jobs can be performed. So the overall objective of long-term scheduler is to strike a right balance between the average rate of process creation and the average rate of rate at which the process departs from the system. So this is a very important role that long-term scheduler plays. Now let us try to understand a short-term scheduler. Now, in contrast to long-term scheduler, a short-term scheduler is called as a CPU scheduler or a dispatcher. So a long-term scheduler, as we have learned, migrates job from job queue to the ready queue. So here a short-term scheduler aims to increase system performance in accordance with which set of criteria by making decisions of which process is to be executed next. Right? Okay. So just see here, short-term scheduler is a program that is capable of assigning the processes to the processor. So the overall objective of short-term scheduler is to enhance or increase the system performance by adhering to a certain set of well-defined criteria for allotting CPU to the processors or deciding on which process to be executed next. So it reduces the degree of multiprogramming, right? So this is also to be understood. It reduces the degree of multiprogramming. Now CPU scheduler selects a process among all the processes in the ready queue and that then allocates CPU to it. So this is a very important task that CPU scheduler performs. So CPU scheduler selects a particular job from a set of jobs that are there in the ready queue and assigns CPU to that particular job. That is, it changes, the process changes its state from ready state to the running state. Right? Okay. So it changes the state of the process from ready state to the running state. Now short-term scheduler are faster than long-term scheduler. Definitely. The short-term scheduler must select a new process from the CPU quite frequently. So it must execute at least one in 100 milliseconds. So this it's a common understanding. So due to the short duration of time between execution, it must be very fast. So just see. Definitely it's called for because the role of short-term scheduler is to assign CPU to the processor, so it should be very fast compared to that of a long-term scheduler. So short-term schedulers are faster than long-term scheduler. So short-term scheduler must select a new process for CPU quite frequently, so it must execute at least one in every 100 milliseconds. So due to the short duration of time between execution, short-term schedulers are expected to be very fast. So in contrast to the long-term scheduler, short-term scheduler takes a job from the ready queue and assigns the processor to it for a given point in time based on certain criteria, right? The overall objective of short-term scheduler is to enhance the system performance or to utilize this CPU optimally. It is responsible for changing the state of the process from the ready state to the running state, and definitely short-term schedulers are faster than long-term schedulers because it is always expected to continuously fetch jobs that are to be executed from the ready queue. Okay, so as it is expected to work at a very high speed, definitely it is faster than long-term scheduler. So now let us move on to a medium-term scheduler. So when a running process becomes suspended. Now suspension of the process may be because of various reasons, right? Suspension of the process may be because of the reason that there is a high priority task that has come in, requesting for allotment of CPU, or a job makes an IO request. So at that point in time, the job has to relinquish the use of CPU. So whenever a job is to be suspended because of the varied reasons, the job is to be placed in the ready queue. Now for such migration, what you need is you need a scheduler. So a running process may become suspended if it makes a IO request. A suspended process cannot make any process towards completion. So this is to be understood. So unless the necessary resource or the interrupted process is not assigned the CPU or not assigned the IO devices, a suspended process may not progress towards completion. So if a process is requesting for IO or a process is interrupted, so definitely it has to be resumed after a while, and then execution has to complete, and then eventually we can call that particular process to be a terminated process. So in this condition, to remove the process from memory and make space for other processes, the suspended process is moved to the secondary storage, and this process is referred to as swapping, and the process is said to be swapped out or ruled out, right? So this is to be understood. Now whenever the process that is waiting for a resource or is waiting for execution, what we need to do is we need to bring out that particular process from the main memory and place it in the secondary memory, and that particular process is called as swapping. So swapping is the process of bringing out or bringing in a process that is waiting for execution, or waiting for or is suspended, and the execution is to be resumed at a later point in time. Now, medium term scheduler is used for the purpose of swapping. So again, I'll repeat it. Medium term scheduler is used for swapping. So there can be two types of operations associated with swapping. So it's called as swap out and swap in. So swap out basically means the process of bringing the process out of the main memory to the secondary memory, whereas swap in basically means the process of bringing in a process from the secondary memory to the main memory for resuming the execution. Okay, so medium term scheduling is used for swapping. So swapping may necessarily improve the process mix because it ensures that the process is optimally utilized. So now here what we have learned is that during the course of execution, a process may be suspended because of the various reasons. So when a process is suspended, then in order to ensure that the process execution completes, the process is to be the process state has to be stored, and it has to be retained in some location. But as said, it cannot stay in the main memory, because main memory can be utilized for storing processes that may that may be executed by CPU. So in order to optimally make use of the main memory, the process that a process or a set of process that has entered into a suspension mode has to be migrated from the main memory to the secondary memory. So the mechanism or the program that is or the mechanism that is involved in bringing the program from the main memory to the secondary memory or back to the main memory is called as swapping. So the program that is responsible for performing swapping is called as medium term scheduler. So medium term scheduler is a program that is responsible for swapping the process in and out of the main memory. So now what we have is we have a sequence of jobs that are placed in the ready queue. So from the ready queue, the jobs enters into they enter into the ready queue. From the ready queue, the job is assigned the CPU, right? The job is assigned the CPU, and the job may enter. So here there's a typo, so it's not ready queue, so it is, if an example, interrupt, or a job is requesting for an IO device, right? So it enters into various modes depending upon what is the task that job calls for. So again, the job re-enters into the ready queue, right? Okay, so once the job is selected from the ready queue and assigned the CPU, so during the course of execution, the job may request for a IO device, or job may be interrupted by some other high priority process. So the job enters into a suspension mode, right? Okay, so if the job enters into the suspension mode, make it rather wait in the secondary memory than to wait in the main memory, because main memory can be used for some other high priority process. So the process, the mechanism of bringing the job out of the main memory and placing it in the ready queue is called as swap out. And likewise, you have a mechanism for bringing in the job from the secondary memory onto the ready queue, that is called as swap in. So swap in and swap out are two activities that are performed by the medium term schedulers for launching the job back onto the main memory. So swap out basically refers to moving the job from the main memory to the secondary storage devices, and swap in basically means a mechanism of bringing the job back from the secondary storage device onto the main memory. So this is the way how the execution of the process resumes. So in today's class, what we have learned about is we have learned about what is scheduling, right? So what is the importance of scheduling? We've learned about who performs scheduling, Then we have learned about different scheduling queues that are there. We have learned about job queue, ready queue, and we have learned about device queue. Then we have learned about what happens when the process actually enters into execution mode. So what may happen? So we have learned that what happens when a process makes a request for IO device, what happens when the time slice terminates, what happens when a high priority process interrupts the execution of the process. We have learned about what happens when the time slice expires. So just see, so we have learned it with the help of very neat schematic representation, where we have shown the flow of control between the jobs and the central processing unit and the ready queue. Then we have learned about what is scheduler and what are the types of schedulers, where we have learned about significance of job scheduler and process scheduler. We have also learned about the hierarchy of process and job scheduler, where process scheduler is a low level scheduler and a job scheduler is a high level scheduler. Then we have learned about schedulers in greater detail. We have discussed categorically, we have discussed three types of schedulers: long term, short term and mid term. And then we have discussed the roles of our long term scheduler, how it controls multi-programming, and then we have learned about short-term scheduler, its role, and the important significance of short-term scheduler. Then we moved on to medium-term scheduler, and then we have discussed the roles of the medium-term scheduler. So thank you very much. So we'll call it a day. Have a very safe day. Thank you very much.